That's good. Thank you for joining me on the stage. So, Thomas is CEO and co-founder of CREAL. I hope I'm saying it right. I think it's CREAL, right?
Yes,
And he'll be telling us about advances in light field display, which I think is also another really interesting class of display. So,
thanks a lot. Good afternoon, everybody. I don't see anyone, but I expect there are people watching or will be in the future. I'm pleased to introduce you to CREAL and to our recent progress with light field display on the way to create a natural display of augmented reality. Let me start with rather mysterious teaser. This is an authentic footage which we took with a camera looking through the AR combiner. And you may notice two pretty peculiar features. So first, some objects are displayed very close in your own hands. And if you tested any other product on the market, this is not really possible to do because the images would be out of focus, and here they are sharp. And the second feature is that when the focus is changing, the sharpness and blur is identical in the real content, here the grass and the hand, and the giraffe. Okay, there is only one object. So in the next video, you will see the changing focus between the planets. When we go closer, the text becomes readable in the hand. So I will explain why it is not possible today without light field or other similar type of displays. And the second thing I want to show you is, of course, it's not possible to just create some display. If it is big box or too ugly or too expensive, it will never really be a product. So I will show you how we combine the light field with the reality with a conventional prescription lens. But let me get back to the beginning, a little bit about the company. We are a 5.5 years old startup based in Lausanne in Switzerland, which is the epicenter of augmented reality hardware here, because this was the place where the smallest smart glasses were designed by Intel and some of the most advanced AR displays designed by Magic Leap. There is also AMS, and we are here. I'm saying it because we inherited enormous experience from Magic Leap and Intel into our team, so we accumulate over a century of trials and errors from other projects. And together, we share the vision of the whole industry that augmented reality will become the next communication platform. It may look like this. The reason is because seeing the digital information in the same way as we see the reality is more natural for our vision, that's how our vision evolved. But it is not more natural today. And not just because it would look strange, but because the 3D visualization is fundamentally flawed. It's unnatural because it's not the same as the real 3D. It's unpleasant, typically within 20 minutes, and it's possibly unhealthy for human vision. And the reason is that the 3D is not complete. So we would like to see in existing products, let's say this bird in front of us, but what we receive are two stereoscopic flat images. So two our eyes perceive the depth, but each one eye sees a flat image in a fixed focal distance. And this is quite underestimated, massive problem for augmented reality because our eyes work like a camera lens and are able and used to focus only at one distance at a time. And this means that we can't focus at the real objects and the content next to each other at the same time correctly. So once you cannot see what the display shows, the display basically doesn't work. And the second problem, more known, is the divergence accommodation conflict comes from the same source, because our two eyes give us the illusion of the presence of the bird in front of us, but they also drive the eye focus to the same distance. And when the brain doesn't receive the sharp image, the eyes of most people start auto-focusing at the image plane of the content, which breaks the natural harmony between how the two eyes see and one eye sees. Most people feel unpleasant eye strain in less than 20 minutes, and that's not really a very long time, considering the future applications should be all-day wearable glasses. So the result is actually worse than wearing someone else's glasses. It's less natural than that. And of course, it's not a problem which we would discover. It's very well known in the industry. We saw something about it in the previous talk as well. And here is, for example, an image from the documentation of Microsoft HoloLens a few years back, which tells the content developers that if you display the content closer than 2 meters, it will become more and more unpleasant because of the vergence accommodation conflict or the focal conflict with the reality. So the solution is to prevent the problem by displaying content far. And in fact, some products even clip the content, so you cannot actually display it close. So to solve the problem, we cannot display just a flat image in a fixed focal distance. We need to provide image or that has volume, that has a focal depth. There are, of course, many different ways to do that, and there is a lot of effort invested first into multifocal displays, then varifocal displays based on eye tracking and some electro-optical element, changing the focus. Holography, again, we saw a little bit about it in the previous talk, which is, however, very difficult to deliver with existing modulators, and light fields. There are, again, multiple flavors of light field, and we do sequential light field, and I will explain you why, and why we think it is actually possibly the best trade-off you can have to deliver the 3D imagery. So let's start with how our eyes work. So first, the world is shining to our eyes light from all possible distances, but our eye is able to focus only one distance at a time on the retina. So either a butterfly or the tree. And of course, there are not only 2 points we need to focus on the retina, it's kind of infinite volume in front of us. And again, we are projecting only one distance at a time. If we want to reproduce such an image artificially, we need to discretize it somewhere. This is what we do. So imagine we discretize the pupil. So instead of having the full light field passing through every point of the pupil, we project only, in this example, 2 viewpoints. And each of them has a very high depth of field. So let's assume it is a basically infinite depth of field. It provides practically always in focus image on our retina. It's independent on the eye focus to a large extent. But each of these perspectives viewpoints provide slightly different perspective image. So a little bit top view, a little bit bottom view. But both of them combined on the retina depend on the eye focus because they entered in a different part of the pupil. And then our eye needs to focus either the two components of the butterfly on one place, which appears then sharp, and the tree is kind of doubled, or we have to focus on the distance of the tree, then the tree overlaps on the retina, and the butterfly becomes doubled. And basically already 2 viewpoints have practically infinite depth resolution, because if we want to display third distance, we have to focus on that distance, on this bird. Of course, if we had only 2 viewpoints, then we could lose one or the other, and blur would be very unnatural because of just this doubling effect. So to make it better, we need to project more of such viewpoints to the eye. And we do typically around 32 viewpoints, which result in already very good blur, and I will show you a bit more photos and videos of that. So how we do it, then there is the focal depth is permanently there. So how we do it technically. So first, I would like to just look at the kind of very top view of that, because we have very different trade-offs compared to other types of light field displays. Here we have rather small number of viewpoints. So as I mentioned, around 32 or even less is okay. But each of them projects high spatial resolution image to the eye, but with only partial color information in it, because many of them enter the eye and the color sums up. And this is how it is realized technically. We have an array of light sources, or basically we have one light source and multiplexer of it, but it works like many light sources, and fast spatial light modulator. It's binary ferroelectric liquid crystal, ultimately our own design. So now imagine what we do is that we flash each light source. There are 3 colors of each of them, reflect it from the modulator, and then split or basically get it back to the eye. And because we created basically small viewpoint due to the small size of the light source, we need to provide a corresponding perspective. So we know what we want to see. We want to see some bird and some butterfly in the tree. So that's exactly what we need to provide. And if we flash another light source, we create a different viewpoint. So it means we need to provide slightly different perspective and so on until we cover the full pupil. And we do this sequence at up to 8.2 kilohertz. The stream of images, of frames, is practically continuous, and the eye is receiving, as far as the human vision is concerned, a completely natural light field. It's independent on the viewer. It's correct even if there is no one. So the eye can change focus, or the camera or animal would still see the correct depth in the projected image. And there is one good big advantage of the system, that because we could form the light field, we can also transform the light field and therefore mimic the function of the prescription lens purely digitally. So no glass needed. If you tell us 35 diopters, including astigmatism, we can correct it with one click, basically. So now I will show you a little bit the history, but also set of products we created. So of course we started with something which was and is a huge, but has basically a retinal resolution, or it's also possible to choose the resolution, and running on the maximum performance. And as I mentioned, finally, I didn't mention it, finally we offer this as a vision care device for a refraction test, the test which tells you your prescription in the eye, but this time this is done purely digitally. I mentioned the fast sequence, so of the images which are bombarding the eye. So this is basically how they look like. Each of them has a very limited color. Okay, these are only black and white, but you can imagine they are red, green, blue. But the combination of them is, I would say, as natural light field as we can achieve with this. So here you see again authentic footage. Camera is looking into the instrument and the camera is changing focus. So now the focus changed from the frog to these branches behind. And even when we zoom in, return back with the focus to the shoulder, we are not really losing the resolution. So then, around 2 years ago, we squeezed the projection system into virtual reality headset, which is a foveated system. So the light field is only in a limited field of view, around 36 degrees, and is complemented by a normal peripheral display spreading up to 100 degrees field of view. And again, we have basically the maximum performance we can deliver with our modulator. And again, here is a footage, authentic, taken by a camera looking inside. So you may notice now that this image, this content, this panel is not sharp until we focus on it. And then we bring in a finger, it's a real time, everything, which is blurred until we focus on it. So again, this focal depth is baked in the projected light. We don't need to know where the camera or the eye is looking. The depth of field will always be correct, defined by your actual own optical system, your own eye. And then we actually very recently squeezed the same performance into the augmented reality headset. If you saw some of my earlier presentations, I was showing this headset, but with a different performance. So now we improved massively, around 8 times if we count, let's say, the number of pixels per second per degree. And again, I will show you, it's basically the same performance as the virtual reality headset. And I will show you some footage from yesterday. So it's quite static, but unless the connection compresses the video, then you should see the resolution. And again, changing the focus between 25 centimeters to 2 meters. And back. So I think we reached the product performance level. What is left is, of course, to make it accessible, cheap, produced in volumes, but also make the different type of product, which I will show you now. So the next step, it's not finished, is to squeeze the projection system into the temple of the glasses. And here you see that the performance is actually the same as the virtual reality headset and the huge box at the beginning. So it's all exercise about scaling down components. So here you can see that in order to make it small, we had to make custom or proprietary basically every single component, starting with the drivers, just image processing drivers, light source with multiplexer, which is a laser with our own microtech device that is multiplexing the light source, our own ferroelectric liquid crystal on silicon, which is 1 megapixel modulator with 7 micron pixels, and freeform projection optics, just piece of glass, and a holographic combiner. So most of these components, all of them we design, and most of them we actually make in-house, including the holographic combiner and the multiplexer. And here is very high level visualization of very obvious way how we get the image to the eye. We reflect the array of the perspectives to the eye from a holographic combiner that is just glued on the prescription lens. And in fact, I have the lens in my hand, and you can see it's just a beautiful, clear glass. And here you can see again, just the exercise with it. So now the projector is running. You see there is very little or no, almost no outward leakage, so the eye is not shining. It's over 92% transparent. And when you get in, you had, in this case, we get 900 nits brightness, but we can go currently above 3,500 nits, and possibly more later. So here again, you see everything is blurred except the bird, because everything is out of focus until we start changing the focus of the camera that is looking inside. So now the focus is far, 3 meters, then we go back. Here, the resolution or the overall quality is not yet kind of full, but we know how many pixels we have there and what we will get out of it in the next 6 months. And now to put the system, or mainly the combiner, into a context of existing combiners. So here you can see that there was a period of time when the holographic combiners were very popular. That was started with Sony, Intel, North, Bosch did some projectors, because it uses normal conventional lens and holographic film. It has all the beautiful properties. It can give you prescription, it's very transparent, it's unobtrusive and very efficient compared to, for example, waveguides. But it was possible to project only basically point-to-point image to the eye. So it created very small or prohibitively small eye box. And this almost certainly became the killing factor of this concept. So that's why waveguides came in or were already around and became the mainstream, because they create a generous eye box. But on the other hand, they sacrifice practically everything else. So classical waveguides, or basically all of those we can buy, make the image flat. No matter what you project in it, inject in it, the output is flat because of pupil replication. It's very difficult to make it aesthetic because it's flat, and also it's quite expensive to make it, so customization is very difficult. It's very difficult to combine it with the prescription on top of it, so something needs to be added. So the divergence accommodation conflict remains because of flatness. Maybe VVQ with Dispelix recently announced waveguide which actually transmits the focal depth, but I think no one has publicly seen it yet. And I will skip the rest because every single parameter has some questionable performance, but the biggest problem is actually the light efficiency. The eye actually receives a fraction of a promille of the injected light. Yes?
Sorry, just to interrupt. I was watching your presentation. I was so absorbed into it that I lost track of time myself. Just to let you know, we're gonna overrun a little bit. So.
Okay.
Yeah,
So this is a last year. So the combiner which we have is basically the same as the first one, but solves the problem of the eye box. So it creates many small pupils which create a big eye box, and therefore combine the beauties of the holographic combiner with a big eye box. And just in summary, so the system for light field with the conventional holographic combiner on the conventional lens provides images with the focus depth, aesthetic lens. It's highly unobtrusive because of no outward leakage, no rainbows. It's highly light efficient, around 100 times more than systems process with waveguides, but also secures high color homogeneity. It does not really limit physically the field of view as harshly as waveguides, and we also don't need to be computing overhead. Thank you.
Yeah, very nice, very nice. Actually, I was so absorbed watching your presentation that I lost track of time myself. So, to the audience, if you have any questions, please type it into the chat box. We will try to ask questions. And I guess so. You mentioned your system is very light efficient, um, but what is the efficiency in terms of computational power and also in terms of power consumption? Because I imagine you have to compute many images from different angles and probably consume a lot of laser power.
Yes, so first, the compute efficiency. This is the first question we often get because there is that mainstream, the misconception that light field really needs just enormously more data and computation. But it's really not true because first, there is a fundamental reason that eye doesn't need more image information from light field than from a flat image, or not more substantial. Because you mentioned we create different images, but they are from 98.9% identical. The change of perspective is a very small pixel shift. So for the compute, we actually use only conventional rendering engine, which provides us just one perspective, and we synthesize the missing ones with around 5% overhead, which is negligible in this context because the rendering can vary by hundreds of percents depending on the content. So the computation is really basically identical. Let's forget of this few percent. And the light efficiency is mainly the result of the high efficiency of the holographic combiner, which concentrates all the light to limited eye box, unlike the waveguides. Waveguides have, okay, just to put it in context, this one gets to the eye up to 50% of the light to the small eye box. Waveguide, after injection, gets 1% typically of the light out, and the eye is taking an additional 5% from that. So if you make a math, there is actually the factor of 100 in the difference. And this is not a small difference because if you get half promille of the light, you need some 200 milliwatts just for the indoor brightness. And that's already too much, even considering like the total power budget. And we need below 10 milliwatts for the light source and indoor brightness, which is okay. There is additional room for the rest of the power budget.
Okay, very nice. We get a question and a comment. He says, congratulations, looks impressive, and according to your presentation, it has many advantages in comparison to waveguides. So why has it not been adopted by all the big players yet? What are the drawbacks?
This is a good question. Okay, the first would be that every technology has its own life cycle and certain level of maturity at every point. So the waveguides were here 20 years or more, I don't know actually. And our tech is becoming mature for a product only now. So that's one reason. Of course, the second reason, that's not a question for me. That's a question for big tech. And I cannot comment on what we know. It's not public anyway. But if we think about what could be like that weak point of it, it's actually the eye box. Because the whole industry is thinking about one size of glass for everyone. So from children to big, or let's say few ranges, but you always need a big eye box just to satisfy different faces and so on. And our eye box is currently around 8 millimeters. So you need certain fitting, at least adjustment of the IPD. And this, as far as we see, was usually the main kind of request which we don't satisfy. But on the other hand, we are convinced that ultimately the glasses will be mass customized anyway, because there's not only a question of the technical performance, but also aesthetics, right? Everything what is on the eyes is a fashion item. So the second reason why you need to customize it is the prescription. Majority of the human of people on the planet need a prescription correction. So you need to provide it. And this one is essentially already a mass customization step. So either you need to buy some inserts and add it on the existing waveguides, but it's probably very difficult to make it aesthetic. In this case, we can just take lens. If you had glasses, we can take your lens, apply that film on it, and convert it into a combiner. So that mass customization step is rather easy.
Can I just ask, so you've developed this beautiful technology and you showcased some things around lenses and eye care and so on. So, what is the actual product? What do you sell?
Yeah, the product is the technology. So, but
Okay.
your previous question said yes, why others didn't adopt it.
Yeah.
So it already partially answers it. We are selling the know-how, the reference design, and the main components, which is actually the silicon chip in it, and the rest we license. But if you think about like the end use, we don't provide a display only for, let's say, glasses. This is probably still far. There is no even content ecosystem. But it starts with that big box. So we provide display for devices which are actually refraction instruments. If you went to the optometrist and you were looking through the lenses and telling, this looks better, that one looks better. In our case, you do it purely digitally.
Hmm.
And then, the same you can do actually with virtual reality headset. We can display you progressive lenses. We can display you any lens you want. We can display you what you will see after surgery or what your children will see if, let's say, their myopia progresses and things like that. So we start on this end, but our ambition is to get the projector into basically consumer AR glasses.
Very nice, very nice. Thank you for the nice presentation. Thank you for answering our questions. I think I enjoyed it, and I'm sure the audience also enjoyed it very much. So thanks a lot for joining us.
Thanks a lot. Sorry for being slow. I thought it would be
No
fast.
problem. I should have told you, but I totally lost track of time. So my mistake, actually. But anyway, we are 10 minutes over time, but now so we have to move on to the next presentation.